Okay, here we look at a Jkff flip-flop. The Jkff flip-flop is the most sophisticated of all the flip-flops that we cover in this class. Here is the symbol for a Jkff flip-flop, and you can see that it's negative edge. It's got a bubble on the clock input. Now it has three inputs, two other inputs in addition to the clock input. One is labeled J, the other K, and then of course, like any flip-flop, the outputs are Q and not Q. Here's the truth table for a Jkff flip-flop. Again, you know what the zeros and ones are. You also know what the X's mean. That means no change, just like it does in an RS flip-flop truth table. And then we got the downward arrow indicating the 1 to 0 transition of the clock. So here, when J and K are both 0, at the time of the 1 to 0 transition of the clock, your outputs are going to stay the same. Okay, so this is the storage condition for the Jk. Okay, here when J is 0 and K is 1, at the time of the 1 to 0 transition of the clock, Q becomes 0 and not Q becomes 1. This is the reset condition. You might remember that with an RS flip-flop, when Q was 0 and not Q was 1, that was also called reset. Here when J is 1 and K is 0, at the time of the 1 to 0 transition of the clock, Q is 1 and not Q is 0. That's the set condition. Okay, so this is all familiar to what we've talked about before, but here's something unique about the Jk flip-flop, and that's when both inputs are 1, at the time of the 1 to 0 transition of the clock, the outputs are going to toggle. So you need to know what toggle means. Okay, well, toggle just means that if Q equals 0 before the 1 to 0 transition of the clock, then Q will equal 1 after. That 1 to 0 transition of the clock. Okay, and then I'll do this in a different color here. Okay, and then if Q equals 1 before the 1 to 0 transition of the clock, then Q will equal 0 after that 1 to 0 transition. So the most succinct, concise way to put this is that whatever value the Q output has before the 1 to 0 transition of the clock, it's going to have its other value after the 1 to 0 transition of the clock. So that's what toggle means. And we'll see an example of toggling in just a moment in a timing diagram for a Jk flip-flop. But before we go to that timing diagram, I just want to talk about what's meant by synchronization and why JKs and also edge-triggered Ds are easy to synchronize. Okay, much easier than trying to synchronize an RS flip-flop. And the reason they're so easy to synchronize is that to synchronize either a JK or an edge-triggered D, you just connect the clock inputs together. So these are all the clock inputs, and you know, I left it vague here because it could either be a JK or an edge-triggered D. But by simply connecting the clocks together, well, now these flip-flops, these edge-triggered flip-flops, are going to be all in step with each other. So, you know, if it's a JK, well, they're all going to be doing their function at the same time, depending on what their J and Ks are equal to. Typically, and we'll see this in the next timing diagram, typically for JK flip-flop, the JK inputs are connected together. And when you connect the JK inputs together, you're either in the top row or the bottom row of the truth table, right? Because if I connect, right, if I short J and K together like this, well, that's going to force the same voltage on both inputs. So I could never have a case of J and K being a different value if they're shorted together. So when I connect J and K together like this, and a lot of times when they're connected together, they're called the T input. Well, I'm either storing data or I'm toggling. So if I connect all the clock inputs together and all the JK's inputs are 1, let's say, okay, they're all 1, well, that means they're all going to be toggling at the same time. Or if I connect these JKs together, okay, call it the T input. So now it could either be a 1 or a 0 on this T input. Well, depending on what the T input is, all these JKs are either going to be storing data if the T inputs are all 0, or they're going to be toggling if the T inputs are all 1. So synchronization is just that the flip-flops are all going to be in step with each other, doing you know, whatever the J and K inputs indicate, you know, what their function is of the truth table at the same time on the transition of the clock. And if it's edge trigger Ds, and we connected their clock inputs together, well, those edge trigger Ds would all be storing data at the same time, or all their outputs would be equaling what their D input is at the same time. Alright, let's look at a timing diagram for JK, and this timing diagram has the J and K inputs connected together. So as I said just a little bit ago, when J and K are connected together like this, we're either in the top row or the bottom row of the truth table for the JK, so we're either going to be storing data or toggling. So you can see here in our timing diagram that all the inputs start out at 0. Now JKs are negative edge, so it's the 1 to 0 transitions that matter. So you see right here during the first 1 to 0 transition, the T input, okay, which again is K and J connected together, are 0. So you can see the Q output remains the same because we're in the top row of the truth table and the JK is storing data. So you see here we had a change in the clock input, and yet the output Q stayed the same. So no change in output here for a change of input, so that's definition of storage of data. Okay, remember the positive edges don't have any relevance here, so the next thing that happens is that, well, you can see right here, now we go into the toggle mode because J and K now are both equal to 1. So after we go into the toggle mode, the first time there's a negative edge of the clock at this time here, well, look, the output toggles. It was 0 before that 1 to 0 transition of the clock, and it becomes a 1 after the time of that 1 to 0 transition. Okay, we continue on, and the next thing that happens is we get a negative edge, a second negative edge, and at the time of that second negative edge we get another toggle. This time the toggle makes the Q output go to 0. Then we get another toggle on this third negative edge where now the Q output toggles back to 1. And then you can see here at this time it goes back into storage state. So during this last negative edge here, the output Q just stays at 1. So again, storage of data occurred. Now, one thing that's very interesting is that during this time where the JK was in toggle mode, look that during the time we had 2 cycles at our clock input. See, from this time here, and remember a cycle is the time it takes for a signal to repeat itself. So you see here's 1 cycle, 2 cycles. So during the time of 2 cycles at the clock input, if you look at what you have at the output here, you have 1 cycle. Okay, so you see 2 cycles, 1 cycle. So if the amount of time here in this interval was, say, 1 second, you would have 2 cycles per second, or 2 hertz at your clock input, and during that same time interval you would have 1 cycle per second, or 1 hertz at your Q output. So you see you get a division of 2 in frequency when JKs are in the toggle mode. And that's a very important characteristic that you're going to see is taken advantage of to make binary counters. And that's the topic of our next video, is counters made out of JK flip-flops doing binary counting.